Hello, guys. So, welcome to our lecture six of the third week. So, today we're gonna, continue our discussion about Boolean functions. Okay, last time we discussed the standard forms of Boolean function, and we discovered that any Boolean function can be represented as sum of product or product of sum, which is very beneficial for hardware implementation because this will result in less delay. Okay, good. Now let's ask ourselves a new question. Okay, if you have any number of variables, Boolean variables, okay, X, Y, Z, whatever. Okay, so how many functions you can construct out of these any variables? Okay, if you have, for example, two variables, how many functions you can construct? Till this moment, we discovered the AND function, which is also a logic gate. It happens that we can make a circuit. This circuit can represent or have the same behavior as this AND logic or AND function. We can do OR, we can do inverter. Also, inverter just need one input. Okay. So basically, you can have 16 out of 2. You can have 16 different functions, like what we see here. So here we have X and Y. They have 4 combinations because we have 2 variables. Okay. So basically, you can construct 16 function, which is 2 to the power of number of the rows or the combinations that XY can make. So X and Y can make 4 combinations. So you can have 2 to the power of 4, which is 16. And how many combination or how many rows that we can get from any variables? Just basically 2 to the power of n. So basically you can have in general 2 to the power of 2 to the power of n different functions. So basically here are the 16 function from function 0 to function 16. Okay, and of course if you have 3 variables you have higher number of functions and so on. But it's good to study the two because basically what you have with three variables is just an extension for what you have with 2 variables. Okay, I mean you will get the same conclusions. And what are these conclusions? Basically, we can have new logic gates. So this is a basic, understanding or the basic insight or the basic takeout from such study is that you can have new definitions or new logic gates. We can say not new definitions, new logic gates. Okay. So of course, each one of those has its own, its own mathematical properties. But we are interested in the ones that we can, implement in hardware. Of course, all of them can be implemented, but some of them can be implemented with one circuit without making a combination of AND and OR and NOT. So this till this moment, every function we studied, okay, and basically every function in logic gates or any Boolean function can be represented using AND, OR, and NOT logic gates, 3 logic gates. Okay, and this is very obvious. For example, if f is just a sum of product, so f is equal to some term here, let's call it term 1 or mi plus mj, just for for the sake of generality. So m is just some literal multiplied or dotted with another letter, dotted with another letter, and so on. Like for example, x dot y dot z bar, and mj the same. It's a letter dot another, and so on. Like for example, x bar dot y dot z bar. And each one of these letters, can be the Boolean variable, or let's say inverter. So for example, x or x bar. So in the definition of the function, we use the OR, In the min term, we used the and in the literal, we used the inverter. So we can construct any function using and or not. Okay, but we now discovered, another logic gates, okay, that can also be represented using one circuit, just like and or not. So there is a circuit that we can implement that represent and gate. There's another circuit, actually many designs that can represent or gate, another circuit that can represent inverter or not gate. Okay, some of these functions, some of these new functions here can also be represented with one logic gate. Okay, so let's discuss these. So basically, here are the 16 functions, all of them. And again, each one of them has its own property, mathematical property. But we're interested in the ones that we can implement using one circuit, not using, and we can of course implement them using and or not, but it will be more beneficial if we represent them with just one circuit, not a combination of other circuits, to reduce cost and power and stuff. Okay, the first one of these is called XOR, or exclusive OR. We call it just, just like XOR. This exclusive is abbreviated as X. This is a new one. Of course, we have here the OR. This is an old one. Then we have the not OR. This is basically not OR. Not OR or NOR. And look at the definition. It is just X or Y inverter. So this is, very clear here if we look back at the truth table. If we look at F7, this is 0, 1, 1, 1. This is basically OR. If we look at F8, it is just equal to F7 inverter. So F8 is just equal to F7 inverter. How we could know this? This is very easy. So 0 here, 1 here, 1 here, 0, 1 here, 0 here, 1 here, 0 here. So this is basically not OR, right? And this is one of the, the second gate that we can implement using one circuit. Also, the exclusive OR or XOR can be implemented using one circuit. Another gate here, it's called the equivalence. But I like to name it XNOR. Just look at the definition. Oh, so this is XOR, X, and this is the operator for the XOR. The equivalence is X, X or Y, then inverter. That's why they call it XNOR. For the equivalence. Okay, and let's look at F6 and F9. So this is F6, 0, 1, 1, 0, and here is F9. It is 1, 0, 0, 1. So this is equal to F6 inverter or prime or complement. The last interesting new function is the NAND, F14, which is not AND, by the way. This is just like the NOR gate, which is not OR. So if this is F1 here, F1 is just AND X and Y. Just look at it. So 0, 0 give you 0, 0, 1 will give you 0, 1 and 0 will give you 0, 1 and 1 will give you 1. If you look at F14, here F1 is 0, 0, 0, 1. F14 is 1, 1, 1, 0, which is F1 inverter or X.Y inverter or prime. And as I said, basically, these new functions are actually new logic gates. I mean, they can be implemented using one circuit. Of course, if we look at the NOR, you can say, okay, we can implement it using OR. Then the output, we take it to boot in the end, something like this. So this is okay, something like this. This is X and Y. Here is X or Y. Here is X or Y inverter, right? But basically, you can make one circuit, not two circuits like this, to make the XNOR. I'm sorry, to make the NOR gate. Same for NAND. You may say that, okay, we can get an AND gate and put the output into an inverter. So this is XY, this will be XY complement. This is NAND. Yes, but these are two circuits. So basically, we can implement this using one circuit. So here is, the list of the new discovered logic gates, we can say. Here is the XNOR, or the exclusive NOR, or they may call it equivalence, but basically the most dominant, naming is XNOR, or exclusive NOR. Here is the exclusive OR, and as you see, they are just inverter of each other. They are complement of each other. The first one XOR is 0, 1, 1, 0. This is 1, 0, 0, 1. Here is the NOR. And if you compare it to the OR, it again inverter. The OR is 0, 1, 1, 1. The NOR is 1 and 3 zeros. And here is the NAND. And again, if you compare it to the AND, they are just, a complement of each other. Okay? One may ask, what is this buffer thing? So this is, not that important in our circuits and design. In our designs. Buffer is basically a circuit that can, enhance a signal, increase its voltage or its power, for example. So it doesn't change the input. The input is X, the output is X. The input is Y, the output is Y. But the output characteristic as a signal, as a circuit, not logic gates, and logic, our logic design is just, have higher voltage. So the signal is good. The signal is, have much strength, we can say, has much power. But basically, we will concentrate on the new discovered ones: NAND, NOR, XOR, XNOR. Okay. So in the next videos, we're gonna take each one of these new discovered, gates, logic gates, logic functions, and try to analyze their properties, their characteristics, their applications, and you will discover a huge, broad applications for all of them. Okay. So thank you very much, guys, for watching this video, and see you in the next videos. Bye bye.